Okay, so welcome back, everybody. Let's begin with a review of what we were discussing last time. Okay, so we were in chapter 4.2. We discussed representing integers in other bases. 1 minute, let me get back to that. All right. All right, so we talked about integer representations in other bases. All right, and we specifically discussed how to write numbers in base 2 or binary, base 8, which is octal, and base 16, which is hexadecimal. Okay, and we discussed how to go from base 10, decimal, our regular number system, to each of these bases, and to do the reverse, to go from these bases to base 10. Okay, and we also discussed how to go from base 2 to base 8 and base 16, and vice versa, from base 8 and 16 to base 2. All right. We also discussed last time a little bit from section 4.3. We talked about prime numbers. All right, what a prime number is, what a composite number is. Okay. I remember a prime number is any integer greater than 1 whose only factors are 1 in itself. Okay. And we also discussed the fundamental theorem of arithmetic. Okay. And remember, the fundamental theorem of arithmetic told us that every integer greater than 1 is either prime or can be written as a product of prime numbers, right? So we could write out its prime factorization, right? So, for example, let's say I have the number 250. If I want to find its prime factorization, right, I could break it up into, let's say, 10 times 25. Okay, 10 I can write as 2 times 5. 2 and 5 are primes. 25 is 5 times 5. Those are all prime numbers. So the prime factorization of 250 would be 2 times 5 cubed. Okay. Okay, so the prime factorization is just where I write an integer as a product of all of its prime factors. Okay, so any questions on anything from last time or homework questions? Okay, let me deal with the homework questions first, then we'll discuss exams after. Okay, I'll come back to that. All right, so let's see, from 4.2, let's do number 5a. Give me 1 second to look it up. Yes, we can discuss that too. All right, let's finish going over the homework problems. Okay. All right, so in 4.2, question 5, you're asked to convert the octal expansion of each of these integers to a binary expansion. Okay. So you're given a number in octal, 572. It's in base 8. All right. We want to convert it to binary. So to convert it to binary, what we are going to do is we're going to take each digit here and convert that to its binary representation. All right. And we're going to write it as a block of three numbers, 3 digits. All right. So 5, 7, and 2. All right. How would I write 5 as a binary number? All right. 5 as a binary number would be what? Does anyone know? Anyone can think of it at the moment? How would I write 5 as binary? 1, 0, 1. All right, that's correct, I believe. We can check that. Okay. Remember, in binary, the number all the way to the right is the number represents the number 1, okay? The next is the 2's place, and then after that is the 4 place, right? It's 2 to the 0, 2 to the 1, 2 squared. So this tells me I've got 1, 1, 0 2's, and 1 4. So 1 4 plus a 1, 4 plus 1 is 5, okay? 7 would be, as a binary number, 1 1 1. That's a 4 plus 2 plus 1, which is 7. 2 would be 0 1 0. Okay, I've got only a 2 there. And I write each one as a block of 3 digits. Okay, so the binary expansion of this number would be 1 0 1. That's the 5. 1 1 1. That's the 7. 0 1 0. That's the 2. And that would be the number in binary. Okay. All right. Any other questions on that, or any other homework questions? Oh, so how do you know when to write it as a block of 2 or 3 or a block of 4? Okay. If you're going from octal, from base 8 to binary to base 2, then it's blocks of 3. If you're going from hexadecimal to base 2, right, base 16 to base 2, then it's blocks of 4.
So anything with hexadecimal, it's blocks of 4.
Yes.
Okay.
All right. Any other questions?
Okay, sir. Like this binary expansion, like how is this like being used in computer science?
Oh, in computer science, well, first of all, everything is in binary, and a lot of times
Yes.
they just write things in different bases for various different reasons. All right, I'm just sort of introducing it to you in your computer science classes. If you have use for it, you'll see it there.
I learned this for subnet masks in like computer networking.
Oh, thank you. Okay, so there you go. You have one application there. Thank you very much. All right, and sometimes in computers, it's convenient to write numbers in different bases for various different reasons. Okay. Okay. Somebody asked, so you asked about 5b, right? So in 5b, that's going back to the question about blocks of 3 versus blocks of 4. In 5, that was part A. In 5b, you're given the number 1604 in base 8, and you're asked to convert that to binary, to base 2, okay? So each digit, again, you're going to go and write each one as a binary number using a block of 3 digits. So 1 would be 001, 6 would be 110, 0 would be 000, 4 would be 100. Okay, so as a binary number, it would be 001, 001, 110, 000, 100. Now, in your book, whenever your book gives you an answer, it always rearranges this into blocks of 4. Okay, that doesn't affect the number, right? So in your book, it would probably look something like this. Maybe something like that, okay? That's the same number. It doesn't matter where you put the spaces. The spaces are irrelevant, okay? The order of the numbers is what matters, not the spaces.
So, sir, it's like, is this like totally wrong if we put the 00 in front?
Oh, you don't even need the 00 in the front. You could put it or you don't need it. Like these 2 zeros here at the beginning.
Yeah.
You don't need them. You can. It's the same thing without them. So I could write this as 111000000100. You could write it like that. Those are called like leading zeros. You don't really need them.
Okay.
Okay. So you can dump them when you're done. All right. Any other questions? Okay. All right. we had two questions regarding the exam. So regarding your second exam, the grades are going up. Some people still don't have them. I haven't gotten them all up yet. So once I finish getting them all up, we can go over it if you guys want. And number two, somebody asked about the final exam. The final exam is not going to be cumulative. Okay, the final exam will only be on the material we've done since the second exam. Okay, so the final exam, which is going to be on chapters 4, 5, and 6, whatever material we do in those chapters. Okay. Any other questions about that and about any of the exams? Okay. There was also a question about the writing project, your assignment, okay, the essay that you have to write. All right. So that assignment is up on Blackboard. You should be able to find it under assignments. When you submit it please through Blackboard. Okay. There should be a rubric online telling you how it's going to be graded. Okay. So again, there's a bunch of questions, topics. You pick the one that you're interested in, that you want to write about. And you're writing me basically just an essay on that topic. So 1 to 2 pages. You research it, write an essay about it, answering the question, and then just put your sources at the end, like a works cited. Okay. And that's going to be due on, I believe I said it's due on the final day of classes. You can check the due date on Blackboard. So whatever our last day is. Okay. All right. Any other questions about that? Okay. Okay, let's see. No, doesn't. I'm not so picky on whatever sources you use. You can use whatever sources you like. Just let me know what sources you're using. Okay. Some of them seem philosophical. Well, it's up to you into how you want to go and get into it. All right. I'm going to leave that a little bit up to you to decide what you want to write about for each topic, as long as you answer whatever question you picked. Okay. MLA format doesn't have to be MLA format. For your sources, just tell me wherever you got it from whatever website or whatever text you got it from. Okay. Okay. So as of right now, I'm not planning to drop any of the quiz grades or the test grades. All right. So it's whatever it says on the syllabus, that's how you'll be graded for at the moment. Okay. A link is okay? Yeah, a link is fine for your sources. All right. All right. All right. Any other questions? Yes, I believe we have still 2 more quizzes. Okay. I want to do a quiz on chapter 4. I'm thinking on Monday, next week on Monday, and then we'll have one more quiz after that. Okay, which we probably will end up doing on the last day of class. Okay.
Are all exam papers graded? I didn't get it yet.
No, they haven't all gone up yet. I'm getting them up. Some of them have gone up, some not yet. So if you don't see those yet, it should be going up soon. Okay.
All right.
Okay. All right. The review for the second exam. Oh, once I get everybody's grade up, then we'll go over it. Okay. Okay. So somebody's asking about the rubric for the writing assignment. When you click on the assignment on Blackboard, it should somewhere say like see the rubric or something like that. You should be able to see it. If you can't find it, let me know and maybe I can send it to you. But it should be there somewhere. There should be like a button you can click and you'll see it. Okay. All right. There's basically, if you're not seeing it, okay, I'll take a look and see if maybe it's not up there. There's basically three things I'm looking for. Number one, the essay should be at least 1 to 2 pages long. Don't make it too long. Just 1 to 2 pages is fine. Okay. It shouldn't just be like one paragraph. It should be an essay. Number two, I should be able to read it. It should make sense. 5 paragraphs. It doesn't. I'm not being so strict about how many paragraphs you need. 5 paragraphs, 6, 3, whatever makes sense for you. Okay. So number one, 1 to 2 pages long. 2, I should be able to read it easily. It should be well written. And 3, you should have at least 2 sources. Okay, that's basically all you need. Okay. Okay. All right. So any other questions about any of that? Okay. Okay. Oh, and of course, it should answer whatever question you picked, whatever topic you picked. Okay. Okay. Oh. All right. Thank you. Okay. All right. So somebody said they have uploaded the rubric to the class Discord, so you can check that out if you want to post the link for everybody, in case anyone doesn't have it yet. Okay. Can we do extra credit work? There's nothing planned for extra credit at the moment. If you have any concerns about your grade so far, you can send me an email. We can discuss it. All right. Okay. All right. Okay, so let's get back to classwork now. Okay. Okay. Each quiz is only like 5% of your grade, so even if you did bad on one of them, I wouldn't worry too much about it. Okay. Okay. All right. Now, don't go by how Blackboard is calculating your grade. Go by how the breakdown I gave you on the syllabus. All right. Okay. 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 So back to classwork. We were in section 4.3. We were discussing prime numbers last time. Today, we're going to discuss the greatest common divisor and the least common multiple. And with that, we will finish off section 4, chapter 4, section 4.3. Okay. All right, so we are still in section 4.3, and we are now discussing greatest common divisor. And the least common multiple. Okay, so for greatest common divisor, I'm going to write GCD for short. Sometimes I'll write it as a capital and sometimes letters and sometimes as lowercase letters. And for least common multiple, as a shorthand, I will write LCM. Okay. All right. So we start with a definition of what the greatest common divisor is. Yes, this is 4.3 continued. Yeah. 4.3 continued. Okay. Okay. So definition for greatest common divisor. Let A and B be integers. Both not both 0. Okay, so at least one of them is not 0. the largest integer d such that d divides a Okay, remember d divides a, that means d is a factor of a, right? So a divided by d is an integer. So the largest integer d such that d divides a and d divides b, okay, meaning d is a factor of a and b, is called the greatest common divisor of a and b. Okay, sometimes it's referred to as the greatest common factor of a and b, right? Factor and divisor mean the same thing. Yeah, okay. Yeah, a lot of the terms that we're seeing in this chapter and even in previous chapters are things you will have seen before in some form or another. Okay. All right. Okay. The greatest common divisor of a and b is denoted as follows. So the greatest common divisor of a and b is denoted by GCD of a and b, like that. GCD of a comma b. So that means the greatest common divisor of a and b. Okay. All right. Let's say I asked you, what is the greatest common divisor of, let's say, 18 and 24? Okay. All right. So one way that we could find their greatest common divisor would be to write out all the divisors of each of them and then find which one is the largest one that they have in common. Okay. So the factors or the divisors of 18, let me write it as a table, and the factors of 24. The factors of 18 are 1, 2, right? 3, 6, 9, and 18, right? 1 times 18, 2 times 9, 3 times 6, all of those give us 18. Okay. The factors of 24 are 1, 2, 3, 4, 6, 8, 12, and 24. Okay, so I'm sure some of you already noticed, what is the greatest common divisor of 18 and 24? Well, they have a few in common. They have 1, 2, 3, and 6 all in common. The greatest common divisor is 6. That's the largest one that they have in common. So the GCD of 18 and 24, that's the largest factor, the largest divisor that they share. So that's 6. Okay, so the answer here would be 6. Is that the same as the greatest common denominator? No. Usually when you're looking for the greatest common denominator, you're looking for the least common multiple of the two denominators, okay, which is what we'll discuss next. Okay, so again, what is greatest common? How did I get 6? So what does the greatest common divisor mean? It means what divisor, which divisor is the largest one that these two numbers have in common. Okay, so for 18, I listed all its divisors, all its factors. Remember, divisor and factor means the same thing. Okay, 24, I listed all its divisors, all its factors. Okay. So which ones do they have in common? 1, 2, 3, and 6. The greatest common divisor is the largest one that they share, that they have in common. So 6 is the biggest one that they both have. Okay, 6 is the largest number that divides both numbers. Okay,
Sir,
Yes.
isn't GCD the same as highest common factor?
Yes.
CF.
I'm not familiar with the term, but it sounds like it's the same. Like greatest common factor I've heard before.
Oh,
That's
okay.
the same thing. Yeah. Okay. All right. So there are a couple of different ways you can find the greatest common divisor. Okay. One of them would be to do this to list out all the divisors of each number. Okay, and then find the greatest one. That's a little inefficient. There are a couple of other ways you can do it. Before I show you those other ways, let me just give you one more definition here. Okay. The integers a and b are relatively prime if their greatest common divisor, I'll write it this way, if the GCD of a and b, the greatest common divisor, is equal to 1. Okay, so two integers whose greatest common divisor is 1 are said to be relatively prime. Okay. All right. So for example, let's say we have the numbers 4 and 9. Okay, what's the greatest common divisor of 4 and 9? 1. Okay, 1 is the largest number that divides both, right? The factors of 4 are 1, 2, and 4. The factors of 9 are 1, 3, and 9. So the greatest common divisor is 1. So 4 and 9 are relatively prime. Okay. Okay. So again, 4 and 9 are relatively prime because the greatest common divisor, the largest integer that divides both, is 1. Okay, so we say that they are relatively prime to each other. Okay. Any other questions? Okay. All right, I want to show you something now called the Euclidean algorithm. The Euclidean algorithm is a method for finding, it's an algorithm for finding the greatest common divisor of two integers. Okay. So it's a step-by-step process that finds the GCD of two integers a and b. All right. Let me describe it to you with an example. So we'll have an example here, and as we go through it, I'll describe the steps of the Euclidean algorithm. Okay. So let's say I ask you to find the GCD of 91 and 287. Okay. Euclid may have been a philosopher. He definitely worked, did math. He was definitely a mathematician. He may have also been a philosopher too. Okay. All right. So using the Euclidean algorithm, if you have two integers, in this example 91 and 287, and you want to find their greatest common divisor, what you do is you start by taking the larger one and dividing it by the smaller one, and you write that out using the division algorithm. Okay, so divide the larger integer by the smaller in the form using the division algorithm. I'll write it that way. Okay. So 287 equals, if I divide by 91, so 91 is my divisor. Using your calculator, if you have one available, you'll see that 91 goes into 287 3 times, so the quotient is 3. And that means that the remainder will be 14, right? 91 times 3 plus 14 gives me 287. Okay, so I have my divisor, my quotient, and my remainder. All right. What we do now, and I be careful here because this is a little bit similar to the algorithm that we did last time for writing a number from base 10 to a different base, but it's slightly different. So try not to confuse this algorithm with the algorithm we did last time, okay? What I'm going to do now is I'm going to take my divisor, 91. The Euclidean algorithm is used to find the greatest common divisor, the GCD, okay? Let me write it here. Find the GCD using the Euclidean algorithm. Let me make it a little clearer. Okay, so step one, we divide here. Step one. Divide the larger integer by the smaller using the division algorithm. Okay. Step two. Okay. What we're going to do next is we're going to divide our divisor, D, 91 in this case, by the remainder. Okay. So step two, divide the divisor, 91, by the remainder, which in this case is 14. Okay, so 91 equals, if I divide 91 by 14, 14 goes into 91 6 times, plus a remainder of 7. So I'm still writing out in this format, okay? So I now have a new divisor, a new quotient, and a new remainder. All right? So I'm going to keep doing this. I'm going to divide my new divisor by my new remainder, and I'm going to keep doing that until the remainder is 0. Okay, so step 3. Keep dividing the new divisor by the new remainder until the remainder r equals 0. Okay. When the remainder r equals 0, then we will stop. All right. So I take 14 divided by my new remainder, 7. Okay. 7 goes into 14 twice, plus a remainder of 0. So the remainder is 0. That means we stop. Okay. The greatest common divisor will be the last non-zero remainder. Okay. So here my remainder was 0. The remainder right before that, the last non-zero remainder was 7. So that is the GCD. So the greatest common divisor will be the last non-zero remainder. Okay. All right. So therefore, the GCD of 287 and 91, the order I write them in doesn't matter, is 7. Okay, so that's our answer. Okay, let's try that one more time. So any questions on the Euclidean algorithm? Okay, so again, it's basically 3 steps. Yeah, I can go back up. Okay. Is that good, or should I go further? Okay, that's good. So again, it's basically three steps. Okay, number one, you divide the larger number by the smaller number, and you write it out in the form from the division algorithm, so you can see the divisor, the quotient, and the remainder. All right, and then you take your divisor, you divide it by the remainder that you got, and you write that out in the form of the division algorithm. And you keep doing this. You divide your new divisor by your new remainder, and you keep going until you get a remainder of 0. And then you stop, and your answer is the last non-zero remainder. Okay, the last non-zero remainder will be the GCD of the 2 numbers. Okay, so let's try another example now. Let's say I ask you to find the GCD of, sometimes I write it as capital letters, like I said before. Let's say I ask you to find the GCD of 414 and 662. Okay, so using the Euclidean algorithm, I'm going to divide the bigger one by the smaller one. 414 goes into 662 one time, quotient of 1, with a remainder of 248. Okay, so divisor, quotient, remainder. I take my new divisor, I take my divisor, 414, divide by the remainder I got, 248. 248 goes into 414 once, plus a remainder of 166. Okay, I take my new divisor, 248, divide by the remainder, 166. 166 goes into 248 once, plus a remainder of 82. Okay. New divisor, 166, divide by the new remainder, 82. 82 goes into 166 twice, right? With the remainder of 2. 2 times 82 is 164, plus 2 gives us back 166. Okay, take my new divisor, 82, divide by my new remainder, 2. 2 goes into 82 41 times, plus the remainder of 0. So, we got a remainder of 0. The GCD is the last non-zero remainder, which in this example is 2. Okay, so that means that the GCD of 662 and 414 is 2. Okay. Good. Questions on that? Okay. All right. We can also find the greatest common divisor of two numbers using their prime factorizations. Okay, so we can also find the GCD of two numbers A and B, two integers A and B, using their prime factorizations. All right, let me again demonstrate how to do this by way of example. All right, let's say I have two integers. Let's say 120 and 500. So let's say I ask you find the GCD of 120 and 500. Okay. All right. So to find the GCD using this method, this is another method I'm showing you here. You first have to write out the prime factorizations. So write the prime factorizations of 120 and 500. So I'll save you the time. I'll give it to you. The prime factorization of 120, if you didn't know it, you could always do a factor tree to get it. But for 120, the prime factorization is 2 cubed times 3 times 5. Okay, that's 120 as a product of all its prime numbers, prime factors. For 500, the prime factorization is 2 squared times 5 cubed. Okay, so the GCD of 120 and 500 is the same thing as finding the GCD of its prime factorizations, right? It's just another way of writing the numbers. So it's the GCD of 2 cubed times 3 times 5 and 2 squared times 5 cubed. Okay, so are you with me so far up to this point before I move on to the next step? Okay, good. So somebody said no, so let's, yeah. So all I've done so far is I wrote out that 120 equals this, its prime factorization, and 500 equals this, its prime factorization. Okay, so I'm just rewriting it with, instead of writing 120 and 500, I'm writing their prime factorizations here. Okay, I didn't have to do that. I just wanted to write it out. Okay. Oh, where did I get the prime factorization from? I'm just giving, in this particular problem, I'm just giving it to you. If I didn't give it to you and you wanted to figure it out on your own, I sort of briefly said this. Let me write it out here. You could figure it out using a factor tree, right? To get the prime factorization, right? So like 120, I can write down as 2 times 60. 60 is 2 times 30. That's 2 times 15. That's 3 times 5. Okay, so the prime factors are 2, 2, 2, 3, 5. So 120 equals 2 times 2 times 2 times 3 times 5. 2 cubed times 3 times 5. Okay. All right. Okay. So once we have the prime factorizations, is it okay to use other methods? Yeah, well, it depends on how the question is worded. If a question asks you to do it a specific way, you have to do it that way. If it doesn't ask you how to do it, if it doesn't tell you how to do it, you can do it however you want. I'm not sure I understand your question. When do we use each? What do you mean? Oh, again, it's really up to you. There's no particular reason to use one over the other. Okay. The truth is, if you have the prime factorizations are not always easy to get. If you have the prime factorizations, could you go up a sec? Yeah, if you have the prime factorizations, then the method I'm showing you now is probably easier. If you don't have the prime factorizations, then the Euclidean algorithm would probably be easier. Okay. Okay. All right. So let me show you the next step now. Okay. So I have the prime factorizations for the two numbers. What I'm going to do now is I'm going to write them on top of each other and line them up. Okay. So write them on top of each other and line up each common prime factor. Okay. So I have 120 equals 2 cubed times 3 times 5. Okay. Below it, I'm going to write 500 equals 2 squared times, there's no 3, so I'm just going to write times 5 cubed. Okay, so I lined up the 2's with the 2's and the 5's with the 5's. Okay, the prime factors are lined up. Okay. I'll write it like that. Okay, so the GCD, the greatest common divisor of 120 and 500. Okay, to get it, after lining it up, what I'm going to do is I'm going to go through each prime factor, starting with 2, then 3, then 5, and I'm going to write down whichever one has the smaller power. Okay, so starting with the 2's, I've got 2 cubed and 2 squared. 2 squared is the smaller power. So I'm going to write down 2 squared over here. Okay, so I'm writing down only the one with the smaller power. Moving on now to the 3's. I have a 3 to the power of 1. And then below it, I've got no 3's. So I'm not going to write anything for 3. Okay, whichever is less. If there's no 3's, that's like having 3 to the power of 0, right? That's a 1. So I'm not going to write anything for 3 because there's no 3's here. Okay. Now I move on to 5. 5, which one has the smaller power? 5 to the power of 1. So I'm going to write 5 to the power of 1, which is just 5. Okay. This product of the primes with the smaller powers is the greatest common divisor. Okay, so the GCD of 120 of 500 is just 2 squared times 5. Okay, and you can leave it like that. That's fine. Or if you want, you can multiply it. Either way is fine. So 2 squared would be 4. 4 times 5 is 20. Okay, so that's the GCD. Okay, so we write down the prime factors with the smaller powers. Okay, and their product is the GCD. Okay. All right. Let me show you one more example of this. Okay. All right. Let's say I asked you, using this method, using the prime factorizations, let's say I asked you the following. Find the GCD of, let's say I give you 2 to the 7th times 5 squared times 11 and 2 cubed times 3 times 11 squared. Okay, so I have two numbers. I've already given you the prime factorizations for each number. Find the GCD, find the greatest common divisor. Okay, so to do that again, I'm going to line them up. 2, 7 times, there's no 3, so I'll make a space for the 3, times 5 squared times 11. And the second one is 2 cubed times 3. There's no 5 in the second one, times 11 squared. Okay, so I've lined them up. I lined up all the common factors. We go with the smaller one. So 2 cubed, 2 to the 7th. The smaller power is 2 cubed. 3 and no 3, so no 3 is less, so I don't write any 3. 5 squared and no 5 is less, so I don't write anything for 5. 11 and 11 squared, 11 is less, so I write down 11. Okay, so the GCD of those two numbers is 2 cubed times 11. Okay, and I'll leave it like that. Okay, so that's it for the greatest common divisor. Let's now discuss the least common multiple. So any questions on the greatest common divisor? Okay. All right, so we're going to discuss the least common multiple now. I'm going to start with the definition. Okay. The least common multiple of the positive integers A and B is the smallest positive integer that is divisible by both A and B. Okay, it's denoted by the LCM of A and B, like that. Okay. Okay, so the least common multiple is basically the smallest number that is divisible by both A and B. Okay, it's the smallest number that the smallest multiple that the two have in common. So, for example, let's say I asked you, find the least common multiple of 10 and 15. Okay. So what are multiples of 10? Multiples of 10 are 10, 20, 30, 40, 50. Okay, what are multiples of 15? 15, 30, 45, etc., etc. Okay, so the least common multiple is the smallest multiple that the two share. All right, so if I were to make a table here, list out the first couple of multiples of 10, its first few multiples are 10, 20, 30, 40, 50, and 60, and etc., etc. Right? The list goes on. The first few multiples of 15 are 15, 30, 45, 60, etc., etc. The list goes on. Okay. The LCM is the smallest multiple that they have in common. In this case, that number is 30. So the LCM of 10 and 15 would be 30. Okay. And somebody had asked before about the denominator, right? Sometimes you want to find a common denominator. That's what you're doing. You're looking for the least common multiple of the two denominators. Okay. All right. So we can find the least common multiple using the prime factorizations in a similar way that we found the greatest common divisor. One moment. So you just keep going until you find a common number. Yeah, but you're looking for the smallest one they have in common. But yeah. Okay. Okay. All right. So like I just said, you can find the least common multiple using the prime factorizations. Okay. Similar to what we did before with the GCD. The only difference is that instead of taking the smaller power, you're taking the larger power. Okay. So we can use the prime factorizations of A and B to find their LCM by using the prime factors with the larger powers. Okay. So let's say I ask you to find the LCM of, let's say, I'll give you the numbers already factorized. So let's say the first number is 2 cubed times 3 to the 5th times 7 squared. And the second number, the prime factorization, will be 2 to the 4th times 3 cubed. Okay. So I'm going to do the same thing I did before. I'm going to line these up and lining up the common factors. So 2 cubed times 3 to the 5th times 7 squared over 2 to the 4th times 3 cubed. And to find the LCM, what we're going to do is write down the ones with the larger powers. Okay. So 2 cubed and 2 to the 4th. Which one is the larger power? 2 to the 4th. 3 to the 5th, 3 cubed. The larger power is 3 to the 5th. 7 squared or no 7. Which one is larger? 7 squared. Okay. So that would be the LCM. Okay, we look at all the prime factors and we take the ones with the larger power. Okay. Any questions on that? Okay. So if there's no questions on that, then I want to finish off this section with just one more theorem. Okay. All right. So the theorem is as follows. Let A and B be positive integers. Then A times B, their product, is equal to the product of their GCD and their LCM. So A times B equals the GCD of A and B times the LCM of A and B. Okay. I'm not going to do the proof, but it sort of kind of should make sense based on the prime factorization methods we just used, right? Because the GCD will have all the smaller powers. The LCM will have all the larger powers. So if you multiply them, that gives you all the factors of A and B. So that would be A times B. Okay. Okay, any questions on that? Who came up with that? I don't know. Okay, why does it work? So I'll leave it for you to figure out, but I sort of gave you a very, very brief explanation of why it works, right? If you go back and like just look at how we found the GCD using the prime factorization method and how we found the LCM, then it should sort of make sense. Should sort of make sense. Okay. Should we know this theorem? Yeah. Yeah, you should know everything we do in class, unless I say otherwise. All right. Okay. Okay. All right. So that is it for everything we're going to do in chapter 4. Okay. Can I summarize that again? Yeah, it's just what it says, that if A and B are integers, then A times B is equal to the greatest common divisor of A and B times the least common multiple of A and B. Okay. All right. Like, for example, let's look at 10 and 15 from above. 10 times 15, according to this theorem, should equal to the greatest common divisor of 10 and 15 and the least common multiple of 10 and 15. Okay, so it should equal to that product. 10 times 15 is 150. The GCD, the greatest common divisor of 10 and 15, is going to be 5. That's the largest number that divides both. The least common multiple of 10 and 15 we saw before was 30. 5 times 30 is 150. Okay. All right. Okay. All right, by the way, you could use this theorem also. If you have two numbers A and B and you know the GCD, you could use this theorem to find the LCM, or the reverse, right? If you have two numbers A and B and you have the LCM, you could use this theorem to find the GCD, right? Just solve for the unknown. Okay. All right. So that is it for chapter 4. Next, we're going to move on to chapter 5, which brings us back to proofs. Okay, in chapter 5, we're going to discuss mathematical induction. Right? Is anyone here familiar with induction? Anyone ever seen it before? Okay. All right. So induction is just another method of proof. It's usually used to prove theorems or statements that are made about the set of integers. Okay, meaning if you have some statement, some theorem that says something is true for all positive integers, or something is true for all non-negative integers, or for all integers greater than or equal to 10, anything like that, you can prove statements like that using induction. All right, so I want to briefly introduce induction, how it works. I'm going to introduce that today, and then we'll go into it in more depth on Wednesday. Okay. Okay, so chapter 5, mathematical induction. Okay. All right. And so in chapter 5, we're going to do two sections, 5.1 and 5.2. Okay. 5.1 deals with induction. 5.2 deals with something called strong induction. Okay. So they're related to each other. Once we finish that, we're going to do a couple of things in chapter 6, and then we'll be done for the semester. We'll be done with the syllabus. No, in chapter 6, there we don't have any proofs. Okay, induction and strong induction will be the last thing stuff on proofs that we do. Okay. So how does induction work? Okay. Okay. All right. And so, like I said before when I was describing it, many mathematical statements or theorems and theorems assert that a property is true for all positive integers. Or sometimes not all positive integers, but sometimes for all non-negative integers. Okay, meaning, so all positive integers would be all integers greater than or equal to 1. Non-negative integers would be all integers greater than or equal to 0. Or sometimes it's you have a statement that's true for all integers greater than or equal to some integer, let's say n. Okay. Okay. Statements of this form can be proven using induction. Okay, so I'll call it induction for short. All right. So what would be an example of a statement that looks like this? Let me give you an example first, and then I will explain how induction works. Okay. So for example, I could have a theorem that states the following. Let's say I have a theorem that says, if n is a positive integer, okay, then 1 plus 2 plus 3 plus ... all the way up to n, that sum is equal to, well, that's actually the sum of the first n positive integers. Does anyone remember what that's equal to? This is, I didn't write it, but that's the same thing as, I write it on the side here. That's the same thing as the sum from I equals 1 to n of I, right? That's ... 1 plus 2 plus 3 plus ... That's a summation formula. Anyone remember what that was equal to? All right, that's fine. I didn't ask you to memorize it anyway. That's equal to n times, oh, did somebody remember? Yeah, all right. It's n times n plus 1 divided by 2, okay? So this here is a statement about all positive integers n. It says for all positive integers n, right? Doesn't matter what n is, the sum of the integers from 1 to n will always equal to n times n plus 1 over 2. Right? That's a summation formula. Okay, so this is a statement. It's a theorem. It's a statement about all positive integers n. Okay, so statements of this form we can prove are true using induction. Okay, so let me describe what induction is, and I don't think we'll get to an example today, but we'll discuss it more next time. Okay, so how does induction work? Okay, all right. So So when I describe induction here, I'm going to give you sort of like a framework or a guideline. In this framework, I'm going to assume that the statement that we're trying to prove is for all positive integers. Okay, but we can adjust it. We can apply it to any statement about any set of integers. All right. Okay, so how does induction work? All right, so to prove that a statement, we'll call it P of n. Okay, where P of n here is a propositional function. To prove that a statement P of n is true for all positive integers n, okay, where P of n, as I said, where P of n is a propositional function, we complete two steps. Okay, so induction, to prove that some propositional function, P of n, is true for all positive integers n, induction has two steps. Okay, step number one is called the basis step. In the basis step, we verify that P of 1 is true. Okay. Or in other words, show that P of n is true for the smallest possible value of n. Okay, so in the way I'm wording this, P of n in this example here that I'm giving you is a statement about all positive integers. So the smallest positive integer is 1, so you would show P of 1 is true. Okay, if the statement was about all non-negative integers, then the smallest non-negative integer is 0, so you would show that P of 0 is true in the basis step. Okay, and we'll go over this again when we do some examples. Okay, so this is the basis step. The first step, you show that your statement is true for the first value that n can be. So if your statement is about all positive integers, the smallest positive integer is 1, so you show that the statement is true when n equals 1. Okay. All right, any questions on that step so far before I continue? Okay, somebody else has to go. We still have 2 more minutes. Okay. The next step is called the inductive step. Okay. So the inductive step works as follows. We show that the conditional statement if P of k, then P of k plus 1 is true for all positive integers k. Okay, and I'm going to make a little note here. And, k has the same, let's say, domain. Has the same domain as n. Okay, so in other words, if your statement is a statement about all positive integers, k is a positive as an arbitrary positive integer. If your statement is about all non-negative integers, k is an arbitrary non-negative integer. Okay, so k is allowed to be whatever n is allowed to be. All right. So in the second step, the inductive step, you show that this conditional statement is true. Okay, that if P of k is true, then P of k plus 1 has to be true. Right? So you would have to do a direct proof for that. Okay. Okay, somebody else has to go. No problem. Take care. All right, so I'm going to discuss this again. I have 1 more minute before everybody goes. I'm going to discuss this again at the beginning of class on Wednesday. Let me just briefly explain why this works. Okay, if you can complete these 2 steps for induction, you have proven that the statement is true. Okay, why? In the first step, you show that P of n is true for the first case, for n equals 1. The second step tells me, if you can prove that the inductive step, the second step is true, the second step tells me that whenever P of k is true, whenever the statement is true for some arbitrary random positive integer k, it also has to be true for the next consecutive integer k plus 1. Okay, so combining that back with the first step, if P of 1 is true, if your statement is true when n equals 1, combine that with the second step. If it's true for 1, then the second step tells me it has to be true for 2 as well. True for k plus 1. Once it's true for 2, the second step again tells me if it's true for 2, it has to be true for the next integer, 3. Once it's true for 3, again, the second step tells me it has to be true for 4. And so this creates like this, like almost like a domino effect. Like once it's true for the first one, it has to be true for all of them. Okay. All right, so we'll discuss this again in more detail next time, and we'll do some examples. Let's get the attendance now, and I will see everybody on Wednesday. Okay, and I'll try and put some homework up for you and finish getting your exam grades up. All right, take care, everybody. Have a good night. Okay. All right, everybody. If you haven't put your name for the attendance yet, please do so now. And I'm going to head out. Take care, everybody.